In section 1.5, we're now ready to start talking about some actual applications of the mathematical techniques, the algebraic techniques that we've been studying. We've learned how to solve simple linear equations. Well, now let's look at a type of real-world problem. Actually, we'll look at several real-world problems where we will end up with equations that do need to be solved using those techniques. Now, the purpose of this section is to help us develop skills in setting up our own equations and then solving those equations. So almost entirely these are application problems. You may know them as word problems or stated problems. That's what we're covering in section 1.5. More specifically, we are going to be talking about the following essential concepts. We're going to learn to solve algebraic word problems using linear equations. We will also look at how to solve a given formula for a chosen variable. I would recommend that we employ the following strategy for solving word problems using equations. The first step in any word problem is to thoroughly read the problem. That is, read it carefully and make sure that you understand exactly what is being asked. We're going to attempt to state the problem in our own words or state what the problem is looking for. You don't necessarily have to write that out on your homework, but you need to be able to state it in your mind at least, that you know what it is that they're looking for. And at that point, let x be the variable, or actually you can choose any variable to represent one of the quantities in the problem. As we look at examples, I'll give you some suggestions on how to decide which quantity to assign to x. If necessary, we are going to write expressions for any other unknown quantities in the problem. Any other unknown quantities. Step 3 would be to write an equation in terms of x that describes the verbal conditions of the problem, much like we did at the end of last section, where we are translating an English statement into something mathematical. Step 4 is, once we have an equation, we now use our skills from previous sections to solve the equation and attempt to answer the problem's question. Last step is always a good idea. In fact, I would require this. You check your solution in the original wording of the problem. Make sure that your solution makes sense and satisfies the actual statement of the problem and not necessarily the equation you came up with, because it's possible that you may have made a mistake in setting up the equation. So if you check your solution in the original wording of the problem, you will be able to confirm that it actually is the right answer to the question. Using these strategies, or these steps, I should say, let's answer the following question. We have that English, French, and Arabic are the official languages spoken in the greatest number of countries. And here's what we know. There are 113 countries in which at least one of these is the official language. All right, so 113, that's going to be some essential information. Okay, English is spoken in 34 more countries than Arabic and 24 more countries than French. We are asked to determine the number of countries in which each of these three languages is the official language. So if I were to restate that in my own words, what I would say is that we have a total number of countries. We know something about how much English, Arabic, and French are spoken in those, but we want to know exactly how many countries speak English, how many countries speak Arabic, and how many countries speak French. Okay, so we have three numbers we're looking for: countries that speak English, countries that speak French. Actually, let's do this in order. And countries that speak Arabic. So Arabic and French. Now here's my suggestion. Anytime you have a word problem like this where you've got three different quantities, you need to let one of them be x. The one that you want to be x is usually the one that the other two depend on. It's the independent variable, while the other two are the dependent variables. In this case, English is spoken in two of the other. Let me try to state that more clearly. You want to let the variable be the one that the others depend on. So in this case, English is something that the number of Arabic depend on, right? It's 34 more than Arabic, and English is 24 more than French. So I'm going to let the number of countries that English is spoken in be the variable x. Okay? Now let's then try to come up with an expression, as it says up here in step 2, for the other two. Now what do we know? We know that English is spoken in 34 more countries than Arabic. Now more than usually means plus, but think about what this means. English has more than Arabic. In fact, 34 more. So how many does Arabic have? It has whatever x is, right, minus 34, right? Because 34 more than this needs to be x. Right? So it's smaller than x. In fact, it's 34 smaller than. And the number of countries in which French is spoken would be x minus 24. Again, it's minus because the number of French countries where French is spoken is less than the number of English, right? Because English has 24 more than French. Okay? So these are the three expressions for each of those numbers of countries. And what's the other bit of information that we know? We know that 113 countries total speak one of these three languages. Now, if I'm going to say total, what does that mean? That means all together, added up. So x plus x minus 34 plus x minus 24 must equal 113. Now we're to an equation. Now, this is what algebra is all about. Algebra is all about figuring out a way to organize complicated information into a symbolic form, so now that we can just apply our mathematical techniques. Once you get to this point, it has nothing to do with countries or languages. It's just variables and mathematical operations, so we can just apply those techniques that we've already covered. We simplify both sides, so I can collect like terms and have x plus x gives me 3x. Minus 24 and minus 34 added together gives me a minus 58. That's still equal to 113. Now if I'm going to try to solve for x, I'm going to get the x by itself by adding 58 to both sides. So it becomes 3x is equal to 113 plus 58 is 171. Divide both sides by 3, and I get x is 171 divided by 3 is 57. Now I can't circle the answer here because I'm not done. I've got to actually answer the question in a word problem. It says determine the number of countries in which each of the three languages is the official language. Now this x represented English. So in English speaking countries we have a total of 57 countries, right? Alright, how many Arabic do we have? Well, we know Arabic is 57 minus 34, so that gives me 23. 23 countries. Okay, and what about French? That's 57 minus 24, which is 33 countries. Now let's check our answer back in the original statement of the problem. First of all, are there 113 total? And I can check that pretty quick with my calculator. Yes, 57 plus 23 plus 33 is 113. So that checks. Alright, is English spoken in 34 more countries than Arabic? 34 more than 23 is 57, so yes. 24 more countries than French? Yes. Right? 33 plus 24 is 57, so yep. We check all of those out. That means there is my final answer. Let's look at the next problem. In 2002, the population of the United States was approximately 288 million, increasing at a rate of 2.4 million people per year. If this trend continues, when will the population be 312 million? So the quantities that we're looking at are the population and the year. Okay, and the question asks what year something will happen. So that's what I'm going to let the x variable represent. It has something to do with which year it happens. Now, because But it's just recommended. It's the easiest way to do this. You've seen a couple of problems phrased this way. What you should do is let x be the number of years since the starting point of this problem, which is 2002. Right? That allows us to have x just represented by smaller numbers for 1, and for each year that goes by, x will increase by 1. So that makes it a nice, easy way to represent x. So x is the number of years since 2002. So if we talked about 2002, x would be 0, and 2003, x would be 1, and so forth. Okay? Now here's what we know. It starts at 288 million and increases at a rate of 2.4 million per year. Okay, so here's how I would write that. 288 is its starting value, plus for every year that goes by, we increase by 2.4 million. Now you'll recognize this word here, per means multiply, so it's 2.4 million per year, which means times x. So this is an expression for the population. What we want to know is what value of x gets me to 312 million. So my equation looks like this. It's 288 plus 2.4x equals 312. Notice how I'm doing population is in millions. That way I don't have to actually write 288 with 6 zeros after it. Just I'll know that the answer from this needs to be in millions. Okay, so now we've got an equation. Once we get to the equation, now it's just solve. So I'm going to solve by getting this x by itself, subtract 288 from both sides. I'm left with 2.4x equals 24. 312 minus 288 is 24. Divide both sides by 2.4, and I get x is equal to 10. Now go back and answer the question. If the trend continues, when will the population be 312? Well, 10 years is my answer for x, but what did x represent? X was the number of years since 2002. So 2002 plus 10 gives me 2012 is when the population will reach 312 million, which is a reasonable answer. In the following example, we are given the following problem. You are choosing between two long-distance telephone plans. Plan A has a monthly fee of $15 with a charge of 8 cents per minute for all long-distance calls. Plan B is $3 monthly charge with 12 cents per minute for long-distance calls. How many minutes of long-distance calls will the for how many minutes of long-distance calls will the cost of the two plans be the same? Alright, so obviously if I make no calls at all, Plan B is cheaper than Plan A. But as the number of minutes increase for long-distance calls, Plan B is getting more and more expensive, so there's at some point where they cross over where the two plans will be equal to each other. So we're asked to find how many minutes is it when they will be equal. Okay, so since we're asking for number of minutes of long distance calls, let's let x be that value. Number of minutes of long distance calls. Alright, so how much does it cost Plan A if x is the number of minutes for long distance call? Plan A is $15 always plus 8 cents per minute. And what do you remember per means? Per means multiply. So 0.08 times the number of minutes. What is Plan B? It's a $3 monthly charge plus 12 cents per minute. So 0.12 times the number of minutes. Okay? And you see this phrase right here. When will they be the same? That means set them equal to each other. When is 15 plus 0.08x equal to 3 plus 0.12x? Now we have our equation. Once you get to this point, you're now ready to just solve for x. So let's move things around. I'm going to move, let's say we subtract 15 from both sides. We're left with 0.08x is equal to negative 12 plus 0.12x. To move the 0.12x over, we'll subtract it from both sides. We'll have a negative 0.04x is equal to negative 12. Divide both sides by negative 0.04 to get the x completely by itself. And I get x is equal to 12 divided by 0.04. Either use your calculator or use the fact that you can move this decimal 2 over. So 1200 divided by 4. It'll be positive because the same sign is going to be 300. And since x is number of minutes, that's what this means, 300 minutes. Okay? And again, you could check your answer to make sure that this makes sense, right? 300 minutes. How much would plan A cost? It's going to be $15 plus 8 cents a minute times 300 minutes. 0.08 times 300. Gives me 15 plus 24, which is $39. The plan B would be $3 plus 0.12 times 300. That's 3 plus 36, which is also $39. So that checks. This is just a way of checking my answer right here. So that proves that my answer, 300 minutes, is correct. In this example, we are given the following statement, that after a 30% price reduction, you purchase a computer for $840. What was the computer's price before the reduction? So we're taking 30% off and we end up with $840. The question is, how much did we start with? Alright, well, here's how I would set this thing up algebraically. We're looking for the original price, so let's let x be the original price. So we know that after reducing it by 30%, we end up with $840. Now, how do you reduce something by 30%? You take the original amount, you subtract 30% of it, right? Now, 30% is 0.3. Remember, you move the decimal 2 places to get the actual decimal number, times the original amount. So 30% of a number is 0.3 times that number. So I'm going to take x minus 0.3 times x, and that is the reduced price. Right? And we know that the reduced price was $840. So that means my equation is x minus 0.3 x is equal to 840. Can I figure out what the original x was? Okay, now I need to solve this equation right here. Alright, so let's simplify both sides. Right, I got to combine these x's together. Remember that if there's no number in front of an x, it's understood to be 1, right? Now 1 minus 0.3, if I combine the coefficients, and so I just get something in terms of x, 1 minus 0.3 is 0.7. Okay, so 70% of x was $840. If I divide both sides by 0.7, x is equal to, see, 840 divided by 0.7. I can plug that into my calculator, or I can move decimal numbers around. I think I end up with $1,200 was the original price. Okay, and you can check if you reduce that by 30%. First of all, 30% of 1,200 would be 0.3 times 1,200, which is $360. So 1,200 minus 360 gives me 840, so it checks out. All right. Okay. At the bottom of the current page in the notes, you'll recognize a series of common formulas for area, perimeter, and volume. Now, you've seen these before, and I stuck them in your notes just so that you have something to refer back to. They're also in a hard copy of the textbook if you happen to have purchased that. Certainly, since it's not required, I'm not expecting you to have that, but these formulas are ones that you should probably be familiar with by now. Maybe not all of them, but some of the most basic ones, like the area of a square is the sides times each other, so s squared. And the perimeter is just adding up the distance around the outside. And so you see a number of examples of how you find area, perimeter, and for those three-dimensional shapes, even the volume. In general, if you see one of these things on a test, I'll provide the formula for you, with the exception of the first four. These you should know. Alright, I'm not going to include those formulas on a test, but the rest of them, if you need them, I will refer them to you as part of the question. I know that in practice, if you ever need to find these areas or volumes or perimeters, you'll be able to look them up. But these are basic enough that you're wasting your time if you have to go back and look them up. You should be able to know something as simple as the area of a circle or a rectangle. Alright, so let's look at an example where you might need to know these formulas to set up the equation. The length of a rectangular basketball court is 44 feet more than the width. If the perimeter is 288 feet, what are the dimensions? So we're asked to find something about a rectangular basketball court, and what we know is that the length is 44 more than the width. Notice how that depends on the width, so that's what I would let x be equal to. Having a hard time writing things consistently today. So x is equal to the width in feet. So what's the length then? If it's 44 more than, now that actually is more than x, so we're going to add to it. Think in terms of which one's bigger, and if it's bigger, add. If it's smaller, you're going to subtract, right? So in this case, that means the bigger side is x plus 44, and the smaller side is x. Now the perimeter for any rectangle is twice the length times twice the width, right? Because there's two widths and there's two lengths. All right, so the perimeter would be 2 times the width, which is x, plus 2 times the length, which is x plus 44. So to get our equation, we're going to take the perimeter and set that equal to 288. 2x plus 2 times x plus 44 is 288. Can we find x for this problem? Now again, it's just an equation to solve, so we go through our steps for solving the equation, which begins with simplify each side. That means I can multiply out this expression, 2x plus 2x plus 2 times 44 is 88, is equal to 288. I can combine like terms, so that's 4x plus 88 is equal to 288. Sorry, I miswrote that. That is 88. Subtract 88 from both sides to get the x term by itself, and I'll have 4x is equal to 200. If we divide both sides by 4, that leaves me with x is equal to 50. Again, I don't just circle the answer. I now need to go back up and answer the question. What are the dimensions? That means length and width. Well, x, according to my statement here, is width. So the width is 50 feet. The length is 44 more than that, or x plus 44, so that is 94 feet. Right? I got this by doing 50 plus 44. Okay? Now you check your answer. Does that make sense? Right? We know that the length is 44 more than the feet, and if I did the perimeter, that would be 50 plus 50, which is 100. And then 94 plus 94, which is 188. 100 plus 188 is 288. That works. Ta-da! we've got the correct answer. Okay? So those are the types of word problems that you're going to be asked to do in this chapter, in this section. There's one other thing we want to talk about, and that's being able to take formulas that are solved for one variable, say for example this one here is solved for p, and rewrite it solved for another variable. Now why would we want to do that? Why do we want to be able to solve formula for one of its variables? Imagine the case where you've got a particular formula that you're using, whether you're doing carpentry work or you're doing something that involves a formula, you're calculating your taxes, or you're a business and you're calculating sales tax, whatever. It might be easier if you're going to have a formula for that if the number that you're always calculating is the one that's solved for. So for example, say I always wanted to find the length, or in this case the width, right? I wouldn't want to plug in perimeter and length and then solve over and over and over again. If I could solve the formula first, then I could always just plug in for P and L and calculate the answer without having to solve the equation every time I use the formula. So being able to rearrange formulas like that can be pretty helpful. Let's do each of these two examples that we have here. By the way, I didn't say it, but it's the same 5 steps for solving linear equations that we learned back in section 1.4. Okay? So for example, the only thing that's different is that we may have variables in there like the L or the P, and we just leave those variables in there and do the operations as though they were numbers. We are asked to solve the formula 2L plus 2W is equal to P. That's the perimeter formula for W. We want to try to get the W by itself. So 2L plus 2W is equal to P. To get the W by itself, we're going to put the W on one side and move everything else to the other. So I would subtract 2L from both sides. End up with 2W is equal to P minus 2L. Notice how I can't combine those because they're not like terms, but I can still leave them in there. That doesn't mean it's incorrect if I can't combine them. I can't simplify it any further. But I haven't got the W quite by itself yet. I've still got a 2 times it, so I'll divide both sides, all of that side, by 2, and I'll end up with W is equal to P minus 2 times L divided by 2. That formula now is solved for W. Okay? Now let's look at one more example that has one little trick in there that you need to be familiar with. Make sure that you can employ this strategy if it ever comes up. In the formula you have in the next example, you're asked to find C, but we've got two different terms that have C's in them. We've got P is equal to C plus MC. Now how do I get the C by itself in this example? Okay, normally if I had numbers in front instead of an M in front, I would just add the two numbers together and I would have a single term of C. Right? The rule that allows me to do that is called this distribution rule, right? If I have A plus B times C, that's AC plus BC. Right? I'm usually going this direction. I just add the two together. Well, I can do the same thing here. Since they both have a C in them, I can write it as something plus something times C. Right? Now clearly the second term is C because I get MC. I know it's a plus. Now what times C is C? Well, clearly that's a 1, right? Isn't that the same thing? C plus MC is 1 plus M added together first times C. Because I could distribute this and go the other direction, which means I can go backwards. I can actually pull the C out of both of those terms. Now I have just something times C. Since that's multiplication, I can divide this thing off. Divide both sides by 1 plus M, which leaves me with C on one side and P all over 1 plus M on the other side. And that formula is now solved for C. Okay? And that's the end of section 1.5, problem solving and using formulas.